Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So we need to draw an interaction diagram, identify the system, and then draw a free body diagram and use dashed lines to connect the members of an action-reaction pair of a soccer ball and a bowling ball having a head-on collision where rolling friction is negligible. So let's get an idea of what this looks like. So first we're just going to do a general sketch, then we're going to do our interaction diagram, identify the system, and then deal with the free body diagram. So our general sketch is you have the soccer ball and you have the bowling ball right next to each other. They're going to be sitting on a surface and the earth is down here. So we can kind of use this to help us with our interaction diagram. So you have the soccer ball. There is a pushing force that is acting on the bowling ball. You have the surface, and the surface is acting on both of those. These are normal forces. So the surface is also acting on the earth. So let's deal with gravity in yellow. So this is going to be a gravitational force. The barbell is going to act on the earth. Sorry, the barbell. The bowling ball, excuse me, is going to act on the earth. So is the soccer ball. So the yellow lines are your gravity. So part B is for the system. The system is just the soccer ball and the bowling ball. So your system is going to be here, not including the surface. Okay, and now our free body diagrams. So let's do the soccer ball on the left, the bowling ball on the right. Give it a coordinate system for both. Okay, so you are going to have the normal force on both of these. So there's going to be a normal force for the soccer ball, a normal force on the bowling ball. When you're dealing with the soccer ball, you are going to have a force that pushes it to the left, and that is the force of the bowling ball on the soccer ball. You're also going to have a force straight down, and that is the force due to gravity. So all of these are on the soccer ball. So you are also going to have the force of the soccer ball on the bowling ball and the gravitational force that is acting on the bowling ball. And then dashed lines to show action reaction. That is going to be force on the bowling ball and force on the soccer ball.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, so we need to draw an interaction diagram, identify the system, and then draw a free body diagram for each object in the system. For a mountain climber using a rope to pull a bag of supplies up a 45-degree slope. The rope is not massless. So let's give ourselves a general sketch and then we'll do an interaction sketch. So this is 45 degrees. Here are that's our bag of supplies. Here is the mountain climber. He's like pulling the supplies up the mountain. Okay. So let's deal with our interaction diagram. So we have the mountain climber. We have the rope. It says it's not massless. So we have to put the rope in there. There's also the supply bag. So this is a pulling force. This is also a pulling force. You have the surface down here. So here's our surface. Here's the earth. The mountain climber is dealing with the surface. The rope is not dealing with the surface, but the supply bag is dealing with the surface. These have normal forces and they have frictional forces. So normal force and frictional force. You also have the earth, which is down here. So we can add in our gravity. So I'm going to do that in yellow. The surface is acting on the earth, or the earth is acting on the surface. The supply bag is acting on the earth. The mountain climber is also acting on the earth. And the rope. So we have gravitational forces, normal forces, and frictional forces. Our system is just the mountain climber, the rope, and the supply bag. So that green box tells us our system. Okay, so now we need to do free body diagrams of the mountain climber, the rope, and the supply bag. So we'll do the mountain climber, the rope, supply bag. So we're at a 45-degree angle. So for all of these, we're going to have y pointing this way and x pointing this way. So our free body diagram for the mountain climber is you have the frictional force, you have the normal force, the force due to gravity is going to pull you straight down, and then you have the tension on the rope. The tension is going to pull out this way. So if you put this on our coordinate system, this is y, x is a little bit further out this way, and this is 45 degrees. Very similar for the rope. Rope, here is y, here is x. The tension pulls a little bit more on this side. The force due to gravity still pulls straight down, and you have, this is negative x, and you have the tension from the mountain climber. And now let's talk about the supply bag. So same thing, let's give it a coordinate system. So y, x, okay. And then the normal force of the supply bag is going to pull it against y. This is a kinetic friction because it's moving. There is a force due to gravity pulling straight down, and then you have the tension on the rope. And then our connections happen, our action-reaction pairs are on the tension. So this tension goes with this tension, and this tension goes with that tension.
Humpuk Pesser? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
So we have a battery-powered toy car that's pushing a stuffed rabbit across the floor. We need to draw an interaction diagram, identify the system, and then draw a free body diagram for each object in the system. So let's get an idea first of what this looks like. So here is your car, here is your rabbit, and it is sitting on a surface. So this is the surface, this is the earth. Okay, so we can tell that the toy car is touching the rabbit. So for our interaction diagram, you have the car, you have the rabbit, there is a pushing force between them. There's also friction. We have the surface down here. The surface is where there is friction, so between the car and the surface there's friction. Between the rabbit and the surface there's friction. There's also a normal force between the car and the system and the rabbit and the system. And then if we are talking about the earth, there is gravity between the car and the earth, the surface and the earth, the rabbit and the earth. So this is our interaction diagram. If we want to know what the system is just the car and the rabbit. Okay, so we also need to do free body diagrams. So while we're doing free body diagrams, let's put an X and a Y axis down. And another one. Okay, so this is your x-axis, this is your y-axis, same on this side. So this is going to be for the car, and this is going to be for the rabbit. So the car has a normal force pointing up. It has the force due to gravity pointing down. It also has the force the rabbit has on the car, FRC, and it has the frictional force on the car. And if you're talking about the rabbit, very similarly has a normal force, has a force due to gravity. The friction here is kinetic friction, so F sub K, and then to the right is the force the car has on the rabbit. So with dotted lines, these are our action-reaction pairs.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
We need to draw an interaction diagram, identify the system, and then draw a free body diagram referring to the figure with the pulley in your textbook. So to start us off, let's do the interaction diagram. So this is block A, this is block B. Between them there is friction. Here is the rope. Between A and the rope there's tension. Between B and the rope there's also tension. Here's the surface. between A and the surface, there is friction. You also have the earth. Between A and the earth, there is gravity. And between B and the earth, there is also gravity. Make our gravity lines in blue. And then we need to identify the system. So the system is just A and B. So that is our system. Now to draw the free body diagrams, it's easier to work with this if we rotate our coordinate systems. So I'm going to rotate it 45 degrees. It's not quite 45 degrees, but it gives us a good idea of what's happening. So this is block B, and this is block A. So in block B, you have the force due to gravity that's going to pull straight down. You have the kinetic friction of A on B. You have the normal force. And you have the tension, A on B. The acceleration is going up. So that makes this our x-axis and this our y-axis. For block A, you also have the normal force. You have the tension B, tension B on A. You have the kinetic friction B on A. You also have the kinetic friction on just A. You have the normal force pulling down B on A, and you have the force due to gravity on A. So our interaction pieces, the kinetic frictions. This kinetic friction will go with this kinetic friction. The normal force will go with the normal force, and the tensions are an action-reaction pair. So this is your free body diagram and your interaction diagram.
हम तक पे sir? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, so we have block A is sliding down an incline. The rope is massless. The pulley is massless. The bearings are frictionless, but the surface is not frictionless. So the rope and the pulley are among the interacting objects, but we need to decide if they're part of the system. So let's start with the pulley at the top. So here is our pulley. So we have block A, block B, the surface, and the earth. So for each block, there's a gravitational force, a normal force, and kinetic friction, and tension with the rope. So let's get those in. So A has gravitational force. B also has a gravitational force. The surface and the earth have a gravitational force. And then there is friction with the surface and a normal force. with the surface. So you also have tension in the pulley. So there's tension for A, tension for B. Okay, so the tension in the massless rope over the frictionless pulley is the same. So the only things that are accelerating are A and B. So only A and B are part of our system. So this is the system. The pulley is not involved in that system. Okay, so here are our free body diagrams. This is for A. This is for B. So this is the x-axis, the y-axis, and on this one, this is the x-axis and the y-axis. Okay, so let's start with the normal force. So the normal force is going to point up the y-axis for both of these. And then the force due to gravity is going to pull straight down. The tension from B to A is going to go up the x-axis. And these two are interacting. And you also have the friction. So friction Fk, and down the x-axis here over Fk. So these are your free body diagrams.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we're looking at an astronaut in a rocket, right, sitting on a chair. I want to find what is the force that the chair exerts. Rather, what is the force that the astronaut exerts on the chair? So first off, we need to find what are the forces acting on the astronaut. So suppose this is the astronaut. First, it has the force due to the chair, and also the force due to gravity. In the first case, the astronaut is not moving, it's at rest, and so the net force must be equals to 0. And what this means is that the force that the chair exerts on the astronaut must be equals to the force that gravity is exerting on the astronaut. By Newton's third law, the force that the chair exerts on the astronaut is equivalent to the force that the astronaut exerts on the chair. Right? This is by Newton's third law. And so this must be equals to the gravity that the force of gravity acting on the astronaut, which is just mg. We're given the mass of the astronaut is 80, so multiply this by 9.81. We get 7.8, that's 10 power 2 newtons. Next, if we, in the other case, we have the astronaut accelerating upwards at 10 meters per second. So the net force that is acting on the astronaut would be 10 meters per second times the mass of our astronaut, right? F equals to ma, and this net force would be equals to the force due to the chair minus the force due to gravity, right? Because in the accelerating case, because it's accelerating upwards, the force of the chair must be greater than the force due to gravity in order for the net force to be upwards. So we can find what is Fc, right? Force steady chair exerting on the astronaut equals to 10 times m plus force due to gravity. And this will give us 80 kg, which is the mass multiplied by 10 plus 9.81. This is 1.6 times 10 to the power 3 newtons. By Newton's third law, this force due to the chair acting on the astronaut is equivalent to the astronaut acting on the chair. Right? So this is the force that is required.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, so we have two strong magnets on opposite sides of a small table. So here is our table. Here is one of the magnets. Here's the other magnet. So the free body diagram, there is a normal force pulling up on the top magnet. There's also a normal force acting on the other magnet. There is the force due to the magnet. And there's a force due to gravity for each of these. Okay, so there is our free body diagram. So we're also told the weight of the table is 20 newtons. The weight of each magnet is 2 newtons, and the magnetic force is 3 times its weight. Okay, so if the magnetic force is 3 times its weight, we have F is equal to 3 mg. So this is the magnetic force on the lower magnet. So you have the normal force of the upper magnet minus the weight minus that force is equal to 0, since this is an equilibrium. So you have the normal force is equal to the weight plus the force, which is equal to the weight plus 3 times the weight. So that's 4 mg. So that's 4 times 2 newtons. So the normal force pointing up is 8 newtons. So we also need the lower force. So F minus mg minus the lower normal force is equal to 0. So the normal force for the lower magnet is 3 mg minus mg, which is 2 mg, which is 2 times 2, or 4 newtons. And then we also need to find the normal force of the table. So for the table, we have 2 times the normal force of the table plus the lower normal force minus the total weight minus the upper normal force is equal to 0, because that's the equilibrium of the table. So this gives us 2 nt is equal to capital Mg, they told us, is 20 newtons. We have the upper normal force, which is 8, minus the lower normal force, which is 4. We're moving everything to the right side of the equal sign. So 2 times that normal force of the table is 24 newtons.
हम तक पे sir? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, so we have a 1,000 kilogram car pushes a 2,000 kilogram truck that has a dead battery. When the driver steps on the accelerator, the drive wheels of the car push against the ground with a force of 4,500 newtons. Rolling friction can be neglected. We need the magnitude of the force of the car on the truck and the force of the truck on the car. Okay, so let's look at a free body diagram. So you have the car. It has a normal force. It has the force that is pushing on C. You have another force. So the surface onto the car. You have the force of the truck on the car. And then we also have the force due to gravity. And with the truck, we also have the normal force, the force of the car on the truck, and you have the gravitational force. So notice there's no surface on this one. Your action-reaction pair is truck on car to car on truck, which is what we're looking for. So we are summing everything in the x direction. So the net force in the x direction is Fs on C minus Ft on C, which is the mass of the car, the acceleration of the car. And for the truck, it is the force C on T equals the mass of the truck, the acceleration of the truck. So knowing all of these, we know that F, the force of the truck on the car, is going to be equal to the force of the car on the truck, since they're action-reaction pairs. So we can say that the force of the car on the truck is, or over the mass of the truck, is equal to the acceleration, because the acceleration of the car is equal to the acceleration of the truck, which is just the acceleration. So plugging this in, we know that combining this equation and the fact that Fc on S minus Fc on T divided by the mass of the car is also equal to the acceleration. So this gives us that the force of the car on the truck is equal to the force of the car on the surface times mass of the truck over mass of the car plus mass of the truck. So plugging in, we know that this is 4,500 newtons times 2,000 kilograms over 1,000 plus 2,000, which is 3,000 kilograms, which is 3,000 newtons. And this gives us our answer. And due to Newton's third law, the force of the truck on the car is also equal to 3,000 newtons.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, so we have blocks with masses 1 kilogram, 2 kilogram, and 3 kilograms are lined up on a row on a frictionless table. All three blocks are pushed forward by a 12 Newton force applied to the 1 kilogram block. So here's that 12 Newton force. It's going to push it to the right. So how much force does a 2 kilogram block exert on the 3 kilogram block? How much force does a 2 kilogram exert on the 1 kilogram? Okay, so first we need to find the acceleration. Since all of these are touching, using Newton's second law, which is mass times acceleration, it's all of the masses, so m1 m2 plus m3, since they are stuck together, is equal to the acceleration. We know the force is 12 newtons. We know all of the masses. So the acceleration is 12 over 1 plus 2 plus 3, which is 2 meters per second squared. So now we have the acceleration of the system. So now it's pretty simple to do the calculations. So force 2 on 3 is the mass 3 times the acceleration, which is 3 times 2, which is 6 newtons. So this is for part A. And then for part B, the 2 kilogram block exerts on the 1 kilogram block. So those are pushing backwards. So force 2 on 1, you have the mass of the second object plus the mass of the third object, since they're both going to push on the first one, times the acceleration, which is 5 times 2, which is a 10 Newton force.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
A massive steel cable drags a 20 kilogram block across a horizontal frictionless surface. 100 Newton force applied to the cable causes the block to reach a speed of 4 meters per second in a distance of 2 meters. What is the mass of the cable? Okay, so we start with looking at forces. So our net force will always be the total mass times the acceleration. So it's a 20 kilogram block. And then we also have the mass of the rope. I'm going to call it m sub r. And this is times the acceleration. So it's a constant acceleration. So you have the acceleration is the total force, so 100 newtons divided by 20 kilograms plus the mass of the rope. And since it's a constant acceleration, it doesn't depend on time, so we can use kinematic equations. So V final squared equals V initial squared plus 2a, the change in position. We were told that this is 4 meters per second. The initial velocity is equal to 0. So we have 2. We just found an expression for the acceleration. and they gave us the change in position as 2 meters. So solving this out, on the left side is 16 meters squared over seconds squared. And on the right side, you're going to have 2 times 2 is 4 times 100, so 400 newtons over 20 kilograms plus the mass of the rope. So we are going to move the 16 over here and move this term over there. So we will have 20 kilograms plus the mass of the rope is 400 Newton meters over 16 meters squared over seconds squared. So this gives us the mass of the rope will be 5 kilograms. So always start with Newton's second law and then realize if it's a constant acceleration that you can use kinematics.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
We need to find the tension in the rope from the figure in your textbook. So we have a person who weighs 60 kilograms pulling down on this pulley. And on the other side of the pulley, you have 100 kilograms. There is tension here, and that tension is the same on this side. So the thing we have to realize here is that the system is in equilibrium. So since the system is in equilibrium, the only thing acting on this is the force due to gravity. And so the tension is equal to the force due to gravity. So remember, force is, for gravity is mg. So we have the mass of the person is 60 kilograms. G is 9.8 meters per second squared. So this is 590 newtons. So remember, always look for equilibriums and use them to your advantage. So an equilibrium is where the net force is equal to 0, so the two opposing forces will be equal.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
So Jimmy has caught 2 fish in Yellow Creek. He has tied the line holding the 3 kilogram steelbed trout to the tail of a 1.5 kilogram carp. He lifts it upwards on the carp with a force of 60 newtons. So we want to draw reaction, action, reaction, free body diagrams. So here is the carp and here is the trout. So on the carp, you're going to have the tension pulling upwards. You're going to have the force due to gravity pulling downwards. And then you're going to have another tension. So for the trout, you're going to have the tension pulling up. So the action reaction is with this tension. So this tension is the same as that tension. You're also going to have another force pulling the trout downwards. and that is the force also due to gravity of the trout. So starting with Newton's second law, you have F net is equal to the mass times the acceleration. So F is equal to the mass of the carp plus the mass of the trout times the acceleration. T2 is pulling up. The mass of the carp is pulling down. The mass of the trout is also pulling down. So those are going to be subtracted. So we can do a little bit of rearranging and solve for the acceleration. So the acceleration is T2 minus m1g minus m2g. So let's write the acceleration up here. T2 minus m1g minus m2g over those masses, m1 plus m2. They gave us m1 is 3, m2 is 1.5, we know g is 9.8, and we know t2 is 60. So plugging these values in, and we get 3.53 meters per second squared. So out here, let's write our givens. T2 is 60 newtons, M1 is 3 kilograms, M2 is 1.5 kilograms, and we know G is 9.8. Okay, so for the trout, if we just focus on the trout, M1 times A is equal to T1 minus M1G. So we need to plug in those values, and we will get that T1 is equal to 40 newtons. So that means F1G, the weight of the trout, is equal to M1 times G. We know M1, we know G. So this is equal to 29.4 newtons. The cart's weight, F2G, is equal to M2G, which is 1.5 times 9.8, which is 14.7 newtons. So T2 is greater than T1, which is greater than force 1G, which is greater than force 2G. And this is how we are ranking these magnitudes.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
A 2-meter long 500 kilogram, so 500 grams is half a kilogram, pulls a 10 kilogram block across a horizontal frictionless surface, and it accelerates at 2 meters per second squared. So they want to know the force that pulls the ice forward and then the rope. Okay, so for the rope, so let's start with the block. For the block, it's the mass of the block times the acceleration. So the mass is 10 kilograms. The acceleration is 2 meters per second squared. So that means that this force is 20 newtons. And then for the rope, the force on the rope is equal to the force on the block plus the mass of the rope times the acceleration. So this is 20 newtons plus 0.5 kilograms times 2 meters per second squared. And this gives us 21 newtons.